I got a couple monitors here, so let me make sure you're seeing the right one. Should see the title slide.
Yes,
Everybody seeing that? Okay, feel free to stop me if there's any issues. I'm happy to answer questions along the way too. Or we can, I don't know, hold to the end, whatever your preference is, but I certainly don't mind if anybody has something that they want to jump in with. So the title of my presentation today is NASA's Atmospheric Propagation Studies and the Return to the Moon. Kind of two different topics there. One at a very high level, the Artemis program to return to the moon, and one very detailed, the propagation studies research that I've been involved in, but hopefully both are interesting in their own ways. And I'm gonna try and do my best to give background on both and do a good job of tying together how they're related. So little introduction about me. I'm Mike. I am in the Advanced High Frequency branch at NASA Glenn Research Center up in Cleveland. I started there in 2011. When I started, I started working in atmospheric propagation, and I've been working in that ever since, and then picked up a couple other areas of research along the way. Propagation, sort of a mundane subject matter to a lot of people, but maybe not to us. I find it interesting, and I think some of the amateur radio folks online probably do too. So in addition to that, more recently, since 2018, I've been working on Gateway and PPE, which you'll find out about coming up here in the rest of this presentation. And then I also have done some work in 3D printed antennas, which is not in this presentation, but I figured I would mention it since it might be of interest. And if you have any questions about it, I'd be happy to talk about it a little bit. Some of my hobbies, there's a lot, electronics, 3D printing, woodworking, homebrewing. Amateur radio is not one yet, but I think it probably will be eventually, just by virtue of the fact that I do it at work. A lot of people that I work with do it, and I do find it interesting. I kind of enjoy collecting hobbies, so I'm sure it won't be long. So let's see, if you're wondering about the connection to Cuyahoga Falls and how I was invited to come speak, I grew up in the Falls actually, right here on the map between Broad and Portage. And I graduated from CFHS in 2006, which is the same year as Katie, Jim Barry's daughter. So I've known Katie for most of school, and actually my now wife has known her even longer. They've been friends since kindergarten, I think. So as evidence of this, I have brought a very embarrassing photo to share. This is all of us at the Harry Potter, the premiere of the last Harry Potter book, I think around 2007 or so, in our wizard costumes, and me with this horrible haircut. So that's my wife, Erin, on the left, and then Katie and Kristen, and of course me. Okay, so moving on to the actual interesting stuff. This is the overview of the presentation that I have today. We have the introduction out of the way. Next up, I have a fancy PR video from NASA that I'm gonna try and show. I don't know how well it's gonna work over Zoom. So if it doesn't work, we can just skip it and I'll send you a link to watch it later. But after that, I'll talk about the Artemis program, which is the program for returning crew to the surface of the moon. I'll talk about the mission profiles of the first two missions, the Cislunar Gateway, which is a space station in lunar orbit, communications with Artemis, the impact of atmospheric propagation on those communications, and then some detail about NASA's atmospheric propagation studies, specifically getting down into the details about the experiment design and how that impacts real communications links, because I thought that might be interesting for this crowd. Okay, so let's see how this works. I'll play it and then feel free to let me know if it's choppy, or I might have to share the computer sound for you to be able to hear it. Let's see. Can anybody hear that while it's playing? Nope. All right,
No.
let's see.
No audio at this point.
There is an option inside Zoom to allow computer audio. It's buried in your audio settings.
There we go. Sounds good. If this doesn't work, I'll move on. But it's far more dramatic and fancy than I could ever be.
Between 1968 and 1970,
Is that working?
Yes, that was working.
Yeah.
Okay.
That's great.
Okay. I'll let it go. It's about 5 minutes.
America launched 9 human missions to the moon, 6 of which successfully touched down, allowing 12 men to walk on the lunar surface. NASA's next chapter of lunar exploration, called Artemis, has the task of not just going to the moon to create a long-term human presence on and around it, but also to prepare for ever more complex human missions to Mars. In short, everything we must be able to do here, we must first do here. So, what will an Artemis mission look like? Everything is designed and tested with our most important element in mind, the astronauts. This is their deep space, human-rated spacecraft called Orion, built in 3 parts. The crew module, where up to 4 astronauts will live and work throughout the flight. The service module, with life support systems for the crew and its own engine and fuel reserves. And a launch abort system, with engines capable of pulling the crew module to safety during launch should anything go wrong. To accomplish the task of launching our crew and heavy payloads, NASA is building the Space Launch System, comprising of a cargo hold, an exploration upper stage, a massive core stage, and 2 extended solid rocket boosters. Altogether, this is the world's most powerful rocket, and it exceeds the legendary Saturn V of the Apollo era in numerous ways. Sitting on the launch pad, the entire rocket, fully fueled, weighs just over 6 million pounds, 5.2 million of which is just the fuel. Once ignited, there is no stopping what comes next. All 4 RS-25 engines and the 2 solid rocket boosters come to life, thundering our crew upwards. 2 minutes after ignition, the solid rocket boosters are spent and released. 8 minutes after launch, the core stage is depleted and separated. The upper stage fires briefly, placing Orion into a parking orbit around the Earth. Here, the crew reconfigure the spacecraft and check systems to confirm everything is ready for deep space travel. With a go from mission control, the crew reignite the exploration upper stage engines to leave Earth entirely. The exact timing of this maneuver is critical to reach a speed that can escape Earth's gravitational pull, but also put Orion on a course that will intersect the moon days later. Once this burn is complete, the upper stage of the SLS is jettisoned and the crew aboard Orion coast for several days toward all that awaits them at the moon. Approaching the moon, we see the fundamental differences between Artemis and Apollo. Instead of requiring Orion to serve as an expendable lunar command module or to carry a constrained lunar lander, the Artemis missions will take advantage of a different approach: pre-staging. Everything needed for lunar missions will be positioned in advance by commercial and international partners. This includes rovers, science experiments, and human-rated systems on the surface. But it also includes a dedicated lunar station in orbit around the moon called Gateway. Here at this station, we can pre-stage a robust lunar lander and establish a strong communications relay. Designed with open standards, the Gateway can be expanded as new missions and partnerships develop, allowing multiple human missions on the moon at the same time and enabling ongoing science to be conducted even between human missions. The Gateway is also capable of adjusting its orbit to allow access to every part of the moon, something the Apollo missions could not do. But the real key in this approach is placing Gateway in a unique halo orbit to perfect the maneuvers needed for Mars missions. And with the growing list of commercial and international opportunities, Gateway is the ideal hub between Earth and all that lies beyond. Returning to our crew as they approach Gateway, the Orion must match the elliptical orbit of the station in order to successfully dock. Once on board, pre-selected crew members transfer to the lunar lander, while those assigned to Gateway remain on station. The lunar lander system itself is built for 3 unique steps: descending from the halo orbit of Gateway down to a low lunar orbit, descending from low lunar orbit to the surface, and once the lunar mission is complete, launching from the surface of the moon and ascending all the way back to the orbiting Gateway. Once back aboard the Orion spacecraft and undocked from Gateway, the crew fire their engine once to break out of the halo orbit and once again to sling the spacecraft around the moon, placing it on a multi-day trajectory back towards Earth. As they near the end of this journey, the service module is released, and the crew module is oriented heat shield first. Entering Earth's atmosphere at 25,000 miles per hour, the friction of air slows Orion considerably, while also subjecting it to temperatures of 5,000 degrees. With the Orion now at just 300 miles per hour, a series of parachutes uniquely tested and produced for this moment deploy, decelerating the craft to just 20 miles per hour for splashdown. With each successful mission, Artemis ushers in the next wave of men and women to explore our moon and prove that together we are ready to go beyond.
All right. So I'll talk a little bit more about Artemis and the different missions. Let me get my slides back up. There we go. So this is just my summary of the video in case it didn't work. So like you saw, the key differences between Artemis and Apollo, essentially that we're going to stay and not just going to visit. So there's the Gateway in orbit. It's called a near rectilinear halo orbit around the moon. And it offers, for one, it offers the opportunity to access different areas of the moon that were never accessible during Apollo. The orbit that it's in kind of spins like a top around the moon. So as it's orbiting, it's also changing in longitude so that you can access any point on the surface. And specifically, there's interest in accessing the South Pole, which is a fairly unexplored region. There's regions on the South Pole where there's craters that never see sunlight, so they're in permanent shadow. And that's one of the interesting areas that we want to explore for water ice. So the plan to return, the first three missions follow this pattern where Artemis 1, scheduled for 2021, next year, is an uncrewed test flight of Orion. So Orion by itself will launch from Earth. It'll go travel to the moon, go into a lunar orbit, stay there for about 6 days in what's called a distant retrograde orbit, and then return to Earth. We'll talk a little bit more about these in the next slides. The second one, Artemis 2, is the first crewed test flight. So 4 astronauts will be on board Orion and will depart for the moon. They won't go into lunar orbit. They'll do just a lunar flyby and then return to Earth. This will be the first time since Apollo 17 in 1972 that astronauts have actually left low Earth orbit. Ever since the last Apollo mission, it's been all shuttle and the ISS and activities that are relatively close to home. So that'll be exciting. Then Artemis 3, of course, will be the most exciting with the first return to the surface of the moon. And the plan there is to have Orion go and link up with the Gateway, which will already be there by that point in 2024. And then descend. Orion will dock with the Gateway. Astronauts will transfer over to the lunar lander systems that are already there waiting for them at Gateway and be able to descend to the moon, to the lunar surface near the South Pole, spend almost a week there, which is almost double the longest Apollo mission. Longest Apollo mission spent about 3 days on the surface. So then ascend back to Gateway, return to Orion, and return home. So the Gateway offers the ability to kind of have a permanent presence there. Astronauts could stay on the Gateway for up to 30 days, doing science missions like they do on ISS, but in lunar orbit. And it also offers a lot of opportunity for reusable vehicles rather than having, like in Apollo, everything that you need for the mission is in one launch and it goes and it comes back and everything's disposable. The goal here is to have reusable landers and vehicles so that, there's always a lunar lander on Gateway and astronauts can go and they can reuse going up and down for different surface missions, possibly even have more than one surface mission ongoing at the same time. So Next up, I have 3 slides that detail the entire mission profile for Artemis 1, 2, and 3. I won't go into too much detail here unless anybody has any questions, but this is pretty much everything you could possibly want to know, I think. One of the things that I find most interesting about Artemis 2 from kind of a research standpoint is it doesn't actually have anything to do with the mission itself, but they're deploying CubeSats at several different stages throughout this mission. I don't know if anybody's familiar with CubeSats and research in that area, but the idea is you know, traditionally space launches, satellites are very expensive, takes a lot of time and engineering, very costly. So the CubeSat initiative is something that's been around for the past, I don't know, 10, 15 years at least, where the idea is to just design small little CubeSats that are, the smallest size is 10 centimeters by 10 centimeters by 10 centimeters cube. And then they can be multiple iterations of that. So either that times 3 in a long stack or times 6 in a 2x3 configuration. But it takes advantage of the fact that all the advances we've had in electronics and miniaturization and things allow us to really make satellites that don't have to be huge, and they don't have to have a ton of, you know, they don't have to have a huge team working on them. So it opens things up for universities and other entities smaller than national space programs to launch satellites. And then they just kind of hitch rides on existing spacecraft. So there's plenty of these that have been launched around the Earth. SpaceX, I know on a lot of the SpaceX launches, they launch a bunch of CubeSats. And it's just like, you know, they'll be launching a satellite for some other purpose. And then they have dispensers that just shoot these things out as it's on its way somewhere else. So what's interesting about Artemis 1 is that it'll be one of the first times that CubeSats will be able to hitch a ride out of low Earth orbit. So you can look up I think there's 13 CubeSats that are planned for this mission. And they all have, you know, some unique way to take advantage of the fact that they're going to the moon, and they can be one of the first CubeSats to do science beyond low Earth orbit. There was actually, it's not officially the first CubeSat out of low Earth orbit, because there was a couple years ago, if you saw on the news, the InSight lander that landed on Mars, that actually carried some CubeSats with it that were part of that mission. They were called Mars Cube 1 or Marco. So those were they went to Mars. They were the official first CubeSats outside of low Earth orbit. But it was really interesting as a communications engineer, because they served as relays during during InSight's landing and descent to Mars. So the nominal operations for InSight were to relay communications back through the Mars Reconnaissance Orbiter, which is in orbit around Mars. But because of the limitations of the communication system on MRO, relaying data that way would have taken about an hour, in addition to the normal 8-minute delay between Earth and Mars. So what the Mars Cube 1 satellites enabled to do was they had a very specific communication system that was designed to be an effective relay for InSight as it was landing, and send that data back on its own, which enabled the mission to watch almost in real time after the 8-minute delay as InSight was landing. So a nice demonstration of what CubeSats can do. I think they called it "Bring Your Own Communications Relay," which was fun. So moving on to Artemis 2, this will be the first mission with crew. So the first time that astronauts have left low Earth orbit since Apollo 17. And they'll do this translunar Earth return, where they just do a lunar flyby within 4,000 miles of the lunar surface and return back to Earth, just to do a checkout of the crewed operations and make sure that everything is functioning as expected for a lunar landing. And then Artemis 3, as you saw, will fly out and match Gateway's orbit in this near rectilinear halo orbit about the moon. Orion will dock with Gateway, and then astronauts will descend in a human lander system from Gateway to the lunar surface, spend almost a week there, and then return to Gateway and take Orion back to Earth. Okay, so Gateway, this is my area. In addition to the propagation studies, this is what I've been working on for the past few years. I'm on the communications team for the power and propulsion element. So we'll talk a little bit about Gateway, what all the different elements are, and then you'll find out what the power and propulsion element is. So like you saw in the video, there's a lot of different reasons for this Gateway concept. You have that access to almost any point on the lunar surface. You have easy ability to do that pre-staging approach where you can send unmanned missions to load up with rovers or anything that you want to take with you, but you don't want to launch on the same mission as your crew. Plenty of opportunities for cargo resupplying. And in addition to all that, with the lunar exploration, it will essentially be a miniature version of the International Space Station in lunar orbit, with the same sort of plans to have our international partners contribute modules to the station and contribute crew to spend up to 30 days there doing research. There's also the possibility of sample return, where lander will go down to the lunar surface, return with samples. They can be prepared on Gateway for return to Earth and then sent back. And then plenty of opportunity for science and technology demonstrations. And one of the functions of PPE that I'm most interested in, since that's my area, is serving as a high data rate communications relay, both for missions to the surface and really anything operating in the lunar vicinity. So altogether, the total crew capacity of Gateway is 4 crew members at any given time, and missions could be 30 to 90 days. In the baseline configurations, there's about 125 cubic meters of pressurized volume for the astronauts to live and work in. So definitely smaller than the station, but station has always also been built up over a much longer period of time. And let's see what else. So the orbit that it's in, you can kind of see a picture of it here. This is that near rectilinear halo orbit that I was referring to. It's called a halo orbit because it has this very elliptical shape where it passes very close to the moon at perihelion, the lowest point of the lunar orbit, and then it spends a very long time swinging out way below the South Pole. And it takes about 6 days to do this entire orbit, with the vast majority of it in this long period where you have almost constant visibility to the lunar South Pole. So in that respect, it's very good for exploration of the South Pole because you're serving as a relay back to Earth. The South Pole isn't always quite so visible from Earth, but you always have Gateway up above that you can use as a relay to send your communications back to an Earth ground station.
Hey, quick question.
Yep.
Did you say there will be rovers and stuff that are put down on the moon before the astronauts go, so they can just, when they do get up there and go down, that they can, access, these different things?
Yeah, that's the plan, is to have the crew missions will launch just with Orion and nothing else. And then all this stuff will be ready and waiting for them there with Gateway, and then with anything on the surface that they might need, like rovers that would just be ready at their landing site. Part of the reason for that is safety concerns that kind of evolved out of some of the shuttle disasters, where there was a motivation to separate crew launches from cargo launches to really maximize safety for the crew launches. And cargo launches, obviously, if something goes awry, it's a disaster, but it's not as bad as if human lives were in danger.
Okay, so they'll actually launch, equipment and have it land on the moon before the astronauts go.
Yep. And one of the other things that's a little bit different is a big push for commercial partnerships. So anybody who follows space news has probably seen, SpaceX and Blue Origin and all these commercial companies that are getting into space flight. And NASA is trying to leverage that in a lot of different ways. So if anybody saw the SpaceX Dragon launch with 2 astronauts to the space station a couple months ago. That was the first manned launch of astronauts on a commercial vehicle. And then we're also trying to leverage very similar partnerships with commercial entities and international entities to do things like ship cargo and ship rovers to the surface and have everything there ready and waiting for the missions. So this is another quick video, just a few seconds really, that shows an animation of the gateway being assembled in orbit. So much like space station, everything will be launched in separate modules that will all meet up in the same orbit and autonomously link together with one another to build the station prior to the astronaut's arrival. So I'll go ahead and play this, and then we can talk about what each of the different modules are. So PPE, well, I'll let it play, and then the next slide has a graphic that'll highlight all these. So this is what's called the phase 1 configuration, which is basically everything that's needed for the first lunar surface mission. And then obviously there's plans to expand with additional capabilities as time goes on. But those elements that you see are kind of the core of the gateway. If I can get my next slide to come up. Here we go. Okay, so this graphic is a little out of date, unfortunately, but I do think it's really good at highlighting what the different elements are. So I'll try and just give you the current information. So the power and propulsion element, that's what I work on. It's the kind of the backbone of the gateway. Provides the solar power with these big solar arrays, provides communications, provides altitude control, and electric propulsion, which is another exciting thing about Gateway, I think, where it has these big solar arrays, and it has this very effective electric propulsion system, which requires much less propellant than traditional chemical propulsion. So it allows it to be much more efficient and move more mass around the moon without requiring as much propellant as a traditional system would, which is similar propulsion systems have been in use for a while, but this is going to be the highest power one that's ever been flown, which is pretty exciting. So that's the power propulsion element. There's no crew space on here, but it provides essentially everything that's needed for the gateway to operate. Esprit is an additional communications and propellant module, which is still planned, but no longer in this position. That's a partnership with ESA, the European Space Agency. So really the next module, like you saw in the previous animation, that docks with PPE it's called HALO, the Habitation and Logistics Outpost, which provides the crew space. So as we're building this up to get ready for astronauts, we have all the power and comm. And then HALO provides the crew space. From what I've heard, it's about the size of a small studio apartment. I guess there's a big mock-up at, I think at Johnson Space Center. But that'll be the primary living space for astronauts while they're docked to Gateway, in addition to the space that's in the Orion vehicle that they arrive in. And then in addition, there's a robotic arm very similar to the Canadarm that was on shuttle and the robotic arms that are on space station for helping to dock these different modules together and install science payloads and do various EVA activities outside the spacecraft. Logistics modules will come, and that's this big yellow guy up on the top, bringing supplies, bringing experiments, both things that might be needed for the lunar surface or experiments that are going to be done in orbit on Gateway. And then as things go on, there's going to be additional habitation modules. So this blue number E here is a habitation module. This is where some of the stuff is getting out of date, but Orion is, as you saw in the video, the crew capsule that brings the astronauts. So altogether, in the previous animation, what you'd really have for Artemis 3 is the PPE, the Halo, the logistics module, Orion, and then some form of lunar lander to get down to the surface, which we'll talk about in a couple slides here. To compare it to the space station, there's a graphic here with both of them to scale. The space station is about the size of a football field, if you include the big solar panels and everything. And relatively speaking, Gateway is a little smaller, but still plenty of room in there for science and exciting lunar surface missions. Okay, so the modules that are currently in development, as the first module to be launched and to provide the framework for the station, the power and propulsion element is underway. That's what I'm, the team that I'm a part of. It is contracted for development with Maxar Technologies. They're a satellite developer. And one of the approaches that NASA wanted to take for Gateway and for the Artemis program, like I mentioned, was leveraging commercial partners in part because we wanted to do things a little bit faster. NASA, like a lot of government entities, can be slow to do things sometimes. And there was a thought that if we contracted a company that builds, telecommunication satellites, they could make some modifications to it and send it to the moon and provide us a framework for the Gateway. So Maxar is our partner for that, for the power and propulsion element. And then that's managed out of Glenn Research Center. So that's the team that I'm on to oversee the communication systems development and work with Maxar as the PPE is being built. The next one is the Halo Habitation and Logistics Outpost that I mentioned. That's currently contracted with Northrop Grumman to provide some living space on the Gateway. The logistics module, the idea is that there would be several, and we could maybe contract with different commercial entities to provide different launches for different missions, but SpaceX was selected as the first commercial provider. So for the Artemis program, they'll be sending up pressurized or unpressurized cargo, science experiments, and any supplies that are needed. And lastly, perhaps most importantly, the Orion crew vehicle is what will actually carry astronauts to the Gateway. This has actually been in development for quite a while, since 2006. It was a part of the Constellation program back then, but it will be the first deep space crew-rated module to leave low Earth orbit since Apollo 17. For Artemis, the anticipation is that it would carry about 4 astronauts, but its max capacity is actually 6, and it can support that many for up to 21 days, or remain docked to Gateway for up to 6 months. The first Orion was actually in Ohio not too long ago. It was flown in for testing at Plumbrook Station in Sandusky. So for those of you who aren't familiar, there's NASA Glenn Research Center in Cleveland. And then we have a satellite facility out in Sandusky called Plumbrook Station that has a lot of the bigger facilities. Originally, the history of that is that it was built out there, and that's where they did all the dangerous stuff, the rockets testing and stuff. So there used to be a nuclear reactor out there too. So they were trying to get it away from the populated areas, which isn't quite the case anymore. But there are still a lot of exciting facilities out there. And the one that they tested Orion in is the Space Power Facility, which is, I think it's the world's largest vacuum chamber. And they put spacecraft in there to simulate the vacuum of space and make sure that everything is operating as expected. So Orion just completed that testing not too long ago. It was kind of a exciting ordeal to watch because they flew it in and they had to fly it in to Mansfield Airport because they did all this research of what routes they could possibly take to Sandusky and if there's any overhead power lines or anything that would get in the way. And the only route that they found that would be successful was from Mansfield Airport to Sandusky. I think they did still end up having to move some power lines or something to fit the spacecraft along the entire route. Okay, So next up, the human lander systems, which obviously will be needed to conduct any surface missions. So the current status of this is that, again, with these commercial partnerships, NASA asks different commercial entities to put together proposals for how they would envision a lunar lander being designed. And recently it was announced that 3 of them, Blue Origin, Dynetics, and SpaceX, were selected to move forward with their designs. So basically what's happening is that we're providing some funding for these entities to develop these concepts and come up with a plan, and then at some point in the future, decide which ones will be built and used for the surface missions. So Blue Origin is the space flight wing of Amazon. Actually, I don't know if they're officially related, but
There'd be enough for that.
But so the Blue Origin proposal is for a 3-stage lander. So essentially there would be docked to Gateway 3 different craft, one called the ascent element, the descent element, and the transfer element. So the transfer element will take the entire craft from Gateway to a low lunar orbit. The descent element will take it down to the lunar surface, and the ascent element will bring the astronauts back to Gateway once the mission's complete. That would launch on the New Glenn rocket system, which is another Blue Origin rocket, as well as the United Launch Alliance Vulcan launch system. I have it labeled here as Blue Origin. It's actually a kind of a team effort called the National Team between Blue Origin, Lockheed Martin, Northrop Grumman, and Draper. So then, in addition, there's Dynetics, which has a proposal for a single structure that acts as both the ascent and descent element. And SpaceX's proposal was also selected to come up with a mission plan using their Starship fully integrated lander that would launch on their Super Heavy rocket. Okay, so getting into communications, the way that we communicate with Artemis or with any other NASA mission are through the 3 networks that NASA has available to us. They're separated by operating regime. So there's the Deep Space Network, which supports anything out at the moon or beyond. There's the Near Earth Network, which supports anything at the moon or closer. And there's the Space Network, which is a network of tracking and data relay satellites that are in geostationary orbit and provide an opportunity for spacecraft to relay through those satellites back to the ground. So the 2 that would be of most use to Artemis are the Near Earth Network and the Deep Space Network. So as we're launching and we're in low Earth orbit and then transiting out to the moon, we would use some combination of those 2 networks to maintain communications. The Deep Space Network has 3 sites that are strategically located around the Earth 120 degrees apart. There's one in Goldstone, California. There's one in Madrid, Spain, and there's one in Canberra, Australia, like you can see on the map up here in the top right. And the reason for that is so that we can essentially maintain coverage with any craft in any direction at any time, no matter what point in its rotation the Earth is at. And that works for deep space because we have, by the time we get out to a certain distance away from Earth, those 3 different sites overlap. So the graphic here down in the bottom right, we have low Earth orbit at 600 kilometers, and then the view from each of the 3 different sites. And the point at which we have full coverage between all 3 is 30,000 kilometers from Earth, which is just a little bit shy of geosynchronous orbit, which is at 35,786 kilometers. So between those, we're able to maintain near constant communication with Artemis, with anything. And as a fun little example of that, I have your Deep Space Network fun fact for the evening. Obviously, when we're talking about communicating with deep spacecraft, we're talking about really, really distant radio links. So I always think it's fun to consider Voyager and how it's the longest radio link in existence. So Voyager 1 currently is the farthest man-made object from Earth. It's now officially outside our solar system, 13.8 billion miles away, and traveling at 10.5 miles a second. So getting farther away every single second. And its downlink frequency is 8.4 gigahertz. So when you do the math to figure out what your free space path loss is at that distance and at that frequency, it shakes out to be about 317 dB. So quite a loss to overcome, and that's not factoring in anything except how far away it is, no atmosphere or anything. The way that those links are closed are with gigantic antennas. So the Deep Space Network has, each of the 3 different sites has these giant 70-meter parabolic dishes. There's additional antennas there too. Each site has 3 34-meter antennas, which can be used for a lot of different things, but generally the Voyager links make use of the biggest dishes. If you can't quite appreciate the scale on this photo, there's a van down here in the bottom the bottom right, so you can kind of picture how big this thing actually is. But yeah, so I think that's amazing that it's still able to communicate from that far away and still operational after over 43 years after it originally launched. We do expect it to keep operating for a little while longer, but the limiting factor there is the power supplied. It's powered by what's called radioisotope thermoelectric generators, or RTGs. And the longevity of those is really what's gonna ultimately force us to lose communication with it. But we are expecting to continue to collect science data from it until about 2025. And engineering data may be possible for maybe another 10 years after that. But ultimately, we're limited by the power. And unfortunately, when you're that far away, solar power is not an option either. So another Deep Space Network fun fact, there is a site called DSN Now, where you can pull up a map of the DSN, all the different antennas, and what they are currently communicating with at any given time. So when I pulled this up the other day when I was putting these slides together, coincidentally, Voyager 1 was downlinking to Madrid. And then you can also see all the other missions that we're receiving or transmitting data. OSIRIS-REx, Advanced Composition Explorer, Trace Gas Orbiter at Mars, MRO at Mars, Juno at Jupiter, MAVEN, and Voyager 2, actually. Both of the Voyagers were communicating when I happened to look at this. So this is the address here if you want to check it out. I can pull it up now and see what happens to be communicating. We have Voyager 1 communicating right now through Goldstone, and Voyager 2 through Canberra, and Stereo A through Goldstone. So you can get different specs on the satellites, images of the satellites, and look up what each different mission is all about. But I just think it's fun that that's available. I like to look at it every now and then, keep it up on a second monitor or something while I'm doing more boring work. Okay, so now getting into a little bit more technical detail. So like I said, one of the projects that I've spent the longest amount of time on is atmospheric propagation research. So when we consider these sites, like for example, the Deep Space Network, these 3 sites in Goldstone, Madrid, and Australia, it's very beneficial to have those 120 degrees apart for visibility reasons, but obviously the climates in all these different places are very different, and that has a big impact on what kind of atmospheric effects you're going to observe with your radio links. Even more so, the Near Earth network has about 15 different sites, and they are even more dispersed. There's one in Svalbard up in the Arctic Circle. There's one in South Africa. They're all over the place, and it's necessary for coverage, but it's also a vast difference in the climates and what you can expect in terms of atmospheric effects at each different site. So it's important to understand those effects when you're designing these links. Obviously, the worst case scenario is that you spend all this money and time to send a spacecraft up, and then you find out that your transmitter wasn't powerful enough and you can't communicate with it. So,
Quick question, Mike.
yeah.
As you move away from Artemis, and maybe you said this and I missed it, is the gateway unit going to be assembled in lunar orbit?
Yes. Yep. So
Okay.
the PPE will go first, and basically everything will go up in a separate launch. PPE will go, Halo will go and dock to PPE. The logistics module will go and dock to Halo. And then finally, when everything's assembled and the lunar landers are there, Orion will take the astronauts and dock to Gateway. But yeah, everything will be assembled in lunar orbit.
And how are you delivering it to the orbit, not with Artemis vehicles, as I understand it?
Yeah, so most of them are, it's probably a different answer for each different element. And I think some of them aren't decided at this point, but some of the smaller ones could go on commercial rockets. Obviously, I think SpaceX is probably planning to use SpaceX rockets. But it's a different answer for each different module. Depending on the mass of the module and which launch vehicles can support that and get it to lunar orbit. But it will be a variety of different launch vehicles.
Thank you very much.
Mm-hmm.
Mike, when they dock these different elements together,
Mm-hmm.
will the machines do it automatically, or will there be somebody on Earth with a camera actually doing that?
It's mostly automatic, but then there's cameras too, just to make sure nothing's going wrong.
I was thinking if we were doing it from Earth, that'd be like the ultimate video game.
Yeah, yeah. And especially out at the moon, you do have the delay. So that's, again, going back to the InSight lander and those Marco CubeSats, that's one of the craziest things to me about those missions is that there's no room for any kind of, human pilot in the mix because there's an 8-minute delay between Earth and Mars. So you have to plan everything and be confident that it's going to work on its own when it gets there.
Okay, thank you.
Mm-hmm.
Oh, Mike, getting back to putting things on rovers and stuff on there, will they be on this gateway thing, and then once it's put together, they'll be launched out of there and land on the moon?
Mostly for surface elements like rovers and things. I think they would launch directly to the lunar surface, just so it's a more efficient use of fuel. But if there is a purpose served by having it go through Gateway, something like a lunar sample return mission, that could go to the Gateway first and be prepped and sent down and back up.
Oh, okay. So basically, if you want a rover up there, you'll just send that up and let it land, and
yep,
be a done deal.
Yep, ready and waiting as soon as you get there, like a rental car.
Okay, sounds good.
Yeah. Okay, so atmospheric propagation. Since I'm not an amateur radio guy, I'm not sure how much of this kind of stuff you guys are familiar with. I know that at most of the amateur radio bands, it's not as significant of an issue as it can be at the higher frequencies like we're targeting for missions like Artemis. So what this graph is the specific attenuation of all the gases in the atmosphere over the frequencies from 1 gigahertz up to 1,000 gigahertz. 100 gigahertz, I'm sorry. Or no, yeah, 1,000. And it's on a log scale on both the y-axis and the x-axis here, so that might be a little bit misleading. But so the specific attenuation is how much loss you would see in decibels for every kilometer that you're propagating through the atmosphere. So when we look at 1 gigahertz, very low, less than 0.01 dB per kilometer. As we start to get higher, there's a lot of advantages to these higher frequencies. Partly that the spectrum isn't as crowded up at those frequencies, and partly, actually, one of the biggest draws is that you can transmit a lot more data. You have a lot more bandwidth relative to your center frequency. But unfortunately, there are also subject to a lot more attenuation through the atmosphere. So the frequency bands that would be of use in Artemis, S-band is used for the rendezvous, proximity operations and docking. So that really would not be coming through the Earth atmosphere. That's the modules communicating with each other as they're in lunar orbit docking. X-band is the command and telemetry, the main link back to Earth. So that's up in the 8 to 10 gigahertz range, and we're starting to see a little bit of atmospheric attenuation at that level. And Ka band is where we have our high rate communications. So trying to actually send back, live 4K video or whatever of the lunar missions, which obviously we want to do, but we need something that can handle that much data. So Ka band is a necessity there, but then it's also much higher attenuation relative to the lower frequencies. So at 22 gigahertz, this is, it's called the water vapor line. That's where water vapor in the atmosphere is absorbing energy near those frequencies. So it creates more attenuation in this little bump here. As we move up higher at 61 gigahertz, we have the oxygen line where the oxygen in the atmosphere is creating a lot of attenuation, and you'd see up to 15 dB per kilometer. And then as you keep moving up, obviously it gets worse and worse and worse. Again, remember this log scale. So by the time you get up to, I should say 1,000 gigahertz. By the time you get up to 1,000 gigahertz, you're looking at 700 dB per kilometer. So it's really prohibitive to actually using those frequencies for space links or links over any kind of distance. That's why as you tend to get higher in frequency, it's usually constrained to shorter link distances. So the portion of the atmosphere that's responsible for these effects is primarily the troposphere, which is the lowest layer from surface level up to about 6.2 miles. And that's if you're looking straight up. So if you're on Earth, I should have asked this earlier. Can anybody see my cursor when I'm pointing at things? Or no?
Yes, it is visible.
Okay. Yeah, so if you're on the surface of Earth and you're looking straight up through the troposphere, you have about 6.2 miles. So you multiply that by your specific attenuation, obviously converting miles to kilometers. And that's how much of a cross-section you're viewing through the atmosphere. As you get to lower and lower elevation angles, if you're watching a satellite that's going past and you want to communicate as it gets closer and closer to the horizon, you're looking through a much, much larger slice of the atmosphere. So communication becomes a lot more difficult unless you can tolerate that extra margin. So just as a quick example, if you're looking at zenith at 90 degrees, you have 6.2 miles. If you're following the same satellite down to 10 degrees elevation, that turns into 35.7 miles. So your attenuation through the atmosphere is going up quite a bit. And this is just the component of the gases in the atmosphere. So depending on the frequency, there's also different interactions with rain or clouds. And particularly at Ka band, the rain component can be quite severe. So that's one of the things that we study with our propagation research activities.
On the previous slide, a quick question. On the previous slide, there are two curves. One of them, I assume, is straight up through the troposphere. The other one is almost tangentially through it.
Yeah, I should have labeled that. I'm sorry. That's these are the differences between wet and dry atmosphere.
Wet and dry. Thank you.
Yeah. So this is the ITU model for gaseous absorption, and you're plugging in some value that represents the amount of moisture in the atmosphere. So like I mentioned, the 20 gigahertz bump is from water vapor. So the blue line is your wet atmosphere. So if you're in a very humid environment, that's you're going to have that extra attenuation from the water vapor. And if it's dry, it's not there because you don't have that vapor present. Okay, so propagation research. One of the things I thought might be interesting for you guys for this presentation is to kind of give the background behind why we study this, and then also walk through the details of how we take these measurements. So the goal of this work is, like I was saying, to study the different climates at different NASA ground stations so that we have a very solid statistical handle on what the climate is like at each different site. There's models for these things, but as you'll see later, the models aren't always as effective as we'd like them to be. So it's always better if you're designing a link and you need to be sure that it's going to work 99.99% of the time, which usually is the case for anything that has humans on it. You want to make sure that you understand that atmospheric component and you're not going to suddenly lose communications when a storm blows in unexpectedly. So to that end, what this project has done has been to set up different receivers at different sites around the world, generally at NASA ground stations, since that's where we're interested in figuring out what the communications are like, and generally at higher frequencies that haven't been as well characterized. Obviously, the lower frequencies that have been in use for long periods of time, these sorts of things have been studied for decades. But as we move into Ka band and higher frequencies, we want to make sure that we understand those just as well. So there's a list of some of the sites here. I have another map in a slide that's coming up where I'll talk about that a little bit more. But generally, we have studied Ka band at 20 gigahertz, Q band at 40 gigahertz, and going a little bit higher up to 80 gigahertz. And lastly, even doing some optical studies. NASA has some upcoming missions that will make use of optical communications to get extremely high data rates. But again, there's a completely different set of considerations there because even just a cloud blowing in overhead can knock out your link. So moving on, I guess one of the things I wanted to mention is that we do take these measurements for NASA's purposes, but there's also a scientific community around it, and we try to participate in that as much as we can. And I'm sure most of you are familiar with the ITU, the International Telecommunications Union, that manages spectrum assignments and all kinds of things related to telecommunications. And we are fairly heavily involved with the study groups of the ITU. They make lots of recommendations on how to model different atmospheric effects or how to model interference between satellites or almost anything you could think of related to telecommunications. So this is one of the places that our work ends up. You know, we collect this data, we submit it to the ITU, and then that helps develop these international models that are used for predicting atmospheric effects all over the world. And then another fun fact here about the ITU. So it's an agency of the United Nations now, as you might expect, but it's actually older by 80 years. The ITU is actually the world's oldest global organization. It was founded in 1865 as the International Telegraph Union, which is 2 decades before Heinrich Hertz proved the existence of electromagnetic waves and 3 decades before Marconi pioneered radio. So it's interesting that it's been around. We think of it today as having such an important role in telecommunications, and it was around for so much longer, doing the same kinds of things for telegraphs before we even knew how to use radio properly. Okay, so moving on, this is a summary of the different sites that we've studied under the propagation efforts. Obviously here in Cleveland at NASA Glenn, we have our test bed where we are setting up our equipment and monitoring different things before we ship it out anywhere else. We have taken measurements at most of the DSN sites. Goldstone in Madrid, Canberra was studied by JPL, which manages the DSN. And then we've also studied White Sands, which is a NEN site, Guam out in the Pacific, which is a space network site where TDRS downlinks, Svalbard up in the Arctic Circle, which is a NEN location. And then there's also been, there's an experiment called AlphaSat, which is managed by ESA with the goal of studying these frequencies, or doing these kinds of propagation studies at Ka band 20 gigahertz and Q band 40 gigahertz. And so we've been participating in that as well. And we have a site in Milan, Italy at a university there, Edinburgh, Scotland, and the Madrid, Spain DSN site is able to take advantage of that satellite to take measurements there. Haleakala in Hawaii is where NASA has a ground station for one of their laser communications demonstrations. So that's where we're taking optical measurements of the atmosphere. And then also Fairbanks, Alaska is an end site where we're taking Ka band measurements. And Andoya, Norway is a planned site for the future. So I figured since you are all radio enthusiasts, it might be interesting to go through what one of these experiments looks like and how we're taking this measurement. So as an example here, I have our site in Milan where we have a 20 gigahertz beacon receiver and 40 gigahertz beacon receiver. So I'll just talk a little bit about that, how it's set up, how we take that measurement, and then give an example of what the data looks like and how we use that. So this is one of those AlphaSat stations that I mentioned. There is a beacon on AlphaSat, 2 beacons at 19.701 gigahertz and 39.402 gigahertz that just transmit at just a continuous wave signal. So there's no modulation, there's no data being transmitted over that signal. It's just purely continuous wave. And that is what we need for an experiment like this because we're mostly interested in what's happening in the atmosphere. So we lock onto that signal and we just measure the power through different atmospheric events and use that to statistically characterize what the atmosphere is doing through different events. So the equipment that we have there, the beacon receivers are really the crux of the experiment where we measure those beacons and monitor the power received. We have antennas, parabolic dish antennas. The Ka band one is 1.2 meters and the Q band one is 0.6 meters in diameter. So both have a gain of about 45 dB with a beam width of just under 1 degree. And then since the AlphaSat satellite is geostationary, so it's generally at one position in the sky, but because it's a little bit inclined, it does move in a sort of figure 8 pattern. And we do need to track it because of that narrow beam width. So we have azimuth and elevation positioners on the antennas that track down to 1/100th of a degree. And then got some RF specs here that I'll talk about in another slide coming up. But in addition to that instrumentation, we also have a water vapor radiometer, which is useful for measuring the clear sky reference level. So with a beacon receiver, there's a beacon on a geostationary satellite and we're monitoring that and we know how much power we're receiving. The water vapor radiometer just looks at the sky on its own and helps us set a reference to determine the absolute power level. So we know, if we normally get minus 100 dBm at the antenna during clear sky, and we know how much it's attenuated relative to that during different atmospheric events, the water vapor radiometer helps us set a reference so that we know, absolutely speaking, how much attenuation we're getting through the atmosphere. In addition to that, we also have a bunch of weather instrumentation that helps us look statistically at rain events and different things and correlate the statistics of those events with the statistics of the radio signals that we're observing through those events. So the dysdrometer is a device that monitors individual droplets for any rain event and then reports back how for any given period of rain, how many droplets of a certain diameter were observed and how many droplets of certain velocity were observed. And we're able to use data like that to correlate that with our power measurements and say, rain isn't necessarily just rain. You can quantify it in terms of how hard it's raining in terms of millimeters per hour, but you can also quantify it in terms of droplet size, droplet velocity, and correlate those things with your signal power to really get a handle on how those types of atmospheric events affect the signal power that you're seeing. Okay, so to talk about the actual RF design of the system, honestly, it's probably going to be boring for some of you guys because it's just, there's no data going through it. It's just measuring signal power. So we're really focused on getting as much fidelity as we can out of that beacon measurement. So we have, like I said, the two beacons are at about 20 gigahertz and 40 gigahertz. We have our two antennas at those frequencies, and then we have low noise amplifiers with about 35 dB of gain. And then we do down conversion, a series of down conversions and filtering, first to 70 megahertz, and then down to 5 megahertz. And then we digitize that with a digitizer card. It's basically an oscilloscope that measures the signal and samples as fast as we reasonably can to monitor that signal and get a sense of what the atmosphere is doing to the power levels. So really the goal of these systems is to maximize the dynamic range that we have available. So if we're monitoring a signal, but as soon as it gets attenuated by 3 dB or so, we lose track of it, that's not very useful because we don't know what's happening for that entire period that we've lost lock on the signal. So we want as high a dynamic range as possible. So the entire system is built around achieving that fidelity. So our low noise amplifiers are really the most important component of the system there. We want a really low noise figure on that and a high gain. And ultimately, for a design like this, we're able to achieve about 40 dB of dynamic range in the system, which is, let me see, if you convert that to linear, it's a linear factor of 10,000. So if you think about it in terms of power, if you would normally receive 1 watt and you want to measure how much that 1 watt gets attenuated, a system like this can track it down to 1/10,000th of a watt. So as you know, if a storm blows in and it's really heavy rain, we do still have events where there's a rain that's heavy enough to completely knock us out and we can't track it at all. But for the vast majority of rain attenuation events, we are able to continue to track the signal and factor that into our data. So what that looks like, I have 2 examples here of very strong rain events. On the left is the Milan receiver that I was just showing you, and on the right is our receiver in Edinburgh. Obviously 2 different events. It's not raining in the 2 places at the same time. But I wanted to show Edinburgh because there's a, coming up later, it was one of the most interesting things that we observed in terms of deviation from what we expected. So really what this is just it's a measurement of our power on both channels, with the red being our 40 gigahertz channel and the blue being our 20 gigahertz channel. So you can tell that as there's a rainstorm blowing in, this was a very heavy rain event, and we tracked it for a while, for about half an hour, and then ultimately, when you see it kind of plateau and hit rock bottom here, that's when we really, there's so much attenuation that we've completely lost track of it. And you can see that in the frequency too, where we're monitoring the frequency of the beacon that we're receiving. And when we completely lose track of it, we really have no idea what frequency it is. So when we take all that, obviously it's, nobody can predict the weather from day to day or from hour to hour. But what you can do to get a good sense of it is look at the statistics over long periods of time. Sorry, my cat is knocking things over. So what we have here is cumulative distribution functions. If anyone has ever taken a statistics class, they basically what it is a graph of for attenuation on the x-axis, how often is that value of attenuation exceeded? So for 0 dB of attenuation, obviously that's exceeded most of the time, about 100% of the time. For 5 dB of attenuation, well, that's we're higher than 5 dB, maybe a couple tenths of a percent of the year. So this is taking all that data and looking at it from year to year and seeing how consistent is it, and on top of that, if we follow the recommendations of the ITU that tells us how to model these kinds of things, how accurate is that model compared to what we're actually seeing with the receiver? And you can see in this case that it is very good. So from year to year, there's quite a spread, maybe a difference of 5 to 10 dB for any given year. But the model is pretty smack dab right in the middle of it, which tells us that it's a good model. And then in addition to that, we also look at things like deviation through different seasons of the year. So down here on the bottom, we have each different month over the 5 years that we were observing this. And you can see that the model's predictions are very good for the temperate months, right? For spring and maybe early fall. But during the summer, when there's maybe a lot of rain, we have much higher attenuation in the model. And during the winter, when it's very cold and not as much rain, much lower than the model would predict. So I mentioned Edinburgh being a little bit different than we expected. So here's the example of that. This is our model, and it is, as you can see, not a good model. So for the 3 years here, 2016 through 2018, we had very, very consistent performance without much deviation from year to year, but the model was still off by about 5 dB. And the reason that we think that is because if anybody has ever been to the UK, it rains all the time. And that's something that the model accounts for. But what we observed at the site was that although it was raining almost every single day, the rain was a lot slower and a lot lighter rain than the model was expecting. So we wound up with this much lower attenuation. And this is the kind of thing where we can take that and we can go back to the ITU and we can help them revise the models and wind up with a much more accurate way to predict what the atmosphere is doing. So that is all I have. I guess that's about an hour even. So I'm happy to take any questions.
I have a couple. Can you hear me?
Yeah, go ahead.
Okay, first of all, those charts that you just showed there towards the end, that almost looked like a cape chart or a cap chart, for is it? That isn't an actual cap, is it?
No, so this is the cumulative distribution function.
Okay.
So we take all the data that we've observed over, in this case, it's over 3 years, and we look at the attenuation that we see on our beacon signal. And this tells us statistically over that period of time, how much attenuation did we observe over that period.
I've done quite a bit with amateur weather watching myself.
Okay.
I do. I look at the projections and I'll tell you what. That's a real similar to these graphs.
Yeah, I bet it is. I mean, because you have to look at it statistically.
A lot of it does predicting of severe storms.
Okay.
When you got a high cape, you got a pretty decent chance of getting storms out of it. The other thing, Elon Musk, very interesting character to me.
Certainly, yeah.
He is, I've heard things where he has talked about putting about 3,000 of those little satellites into orbit.
Yeah, yeah.
What's that going to do for launching?
That's a very good question. So you're talking about Starlink, I think.
Yeah.
So they have a plan, and it's not just SpaceX even. SpaceX is one of the companies at the forefront of it, but there are other companies with similar plans. They want to launch these, it's called a constellation of satellites in Earth orbit with the intent that you would always have coverage at different points on the Earth and always have very good data rates. So like in SpaceX's case, they want to use Starlink to provide satellite internet. Basically anywhere on the globe that you are, you would be able to see a Starlink satellite and get internet through it. But you're right, there's, I think currently, I actually was just reading up on this for a different reason, but I think that SpaceX is approved for 12,000 satellites through the FCC, which is huge. And that's not even everything in the constellation. I think their ultimate constellation is planned to have 48,000 of these Starlink satellites.
If you put that much stuff in an orbit that's already polluted with all the garbage over the last 40 or 50 years, how the hell are you ever going to be able to launch anything?
Yeah, it's a big problem. There's the space junk problem. And so part of the ways that they try to mitigate that is that part of the approval process for getting approved to launch it is to have some kind of deorbit plan. So
I would really think they'd have to do something like that.
Yeah.
I saw there was a video that I actually do a podcast that's on technology and ham radio on Sunday evenings.
Okay.
And I saw a clip of that I got off of YouTube that was talking about space junk.
Yeah.
And what it was talking about was not only that, it talked about Elon Musk's idea. And there was a thing that said that they had launched Apollo 12 launched a piece of the rocket towards the sun thinking it would burn up. It ended up going around the sun and coming back, and it's orbiting a planet now.
I've heard stories like that where they think they've discovered a new asteroid or something, and it turns out it's a spent stage of Apollo. And now, a few years ago, as part of their test flight for the Falcon Heavy, I know Elon Musk launched one of his Tesla cars.
Yeah, I saw that. With a spaceman in it and everything.
Yeah. Yeah, he's definitely a showman, that's for sure.
When do you think we'll be on Mars?
So NASA's official plan is the 2030s, with the plan that we would do everything that we need to demonstrate with Artemis in lunar orbit and on the lunar surface, and be able to develop our technology there and then apply that to Mars missions. It's another aspect of that near rectilinear halo orbit is that it's basically an orbit around the moon, but just barely. So you can, it provides an easy way to depart from Gateway and go to the lunar surface, but it also provides an easy path to depart from Gateway and go on a mission to Mars.
Mars, yeah.
Yeah. So that's why that's the name Gateway. That's where that comes from. Is that it would be,
I think if Elon has his way, it's going to be sooner than that.
Yeah, I'm sure Elon would love to beat NASA there.
There was another.
That's his goal.
There was another vehicle that I saw blew up here. Was launched out of Alaska, I think it was. The project name started with an A, but I don't think it was Artemis.
Yeah, I'm not familiar with that. Artemis is going to be launching from the Cape down in Kennedy.
This was, I think it was support for the lunar stuff and that. You know, it was another company trying to come on.
Yeah, I'll have to look that up.
They had got about halfway into orbit, and the thing blew up. And I believe it was launched out of Alaska.
Okay. Yeah, I know there was also so the SpaceX launch that sent the astronauts to the station. There was also a contract with Boeing for their space capsule. And they ran into some issues a couple years ago with one of their test flights that had some technical difficulties. So SpaceX wound up being the first ones to do it. But Boeing is still proceeding with that.
I think it's interesting that this is going to get commercialized as quickly as it is. I heard a thing yesterday that said Tom Cruise is going to fly in SpaceX to go up to the space station to do a movie. That's happen within the next couple of years.
Yeah, I think NASA's starting to see that maybe it's another revenue stream, possibly.
Why not? Why
we
not?
need the increase in the budget.
All right. Anybody, go ahead and take other questions. I'll shut up now.
Mike Frank here, W8EZT. Question and a comment. I'm assuming at these frequencies, 1 gigahertz and above, the ionosphere is not a factor in those frequencies?
Yeah, that's right. It's well, especially at we're mostly talking about 20 gigahertz at Ka band, and yeah, basically transparent. We're mostly interested in the tropospheric effects from all the different weather phenomena.
Thank you. Just a general comment. I think a lot of the hams were either in their teenage years or early 20s when the original Apollo 11 or Apollo series and space program was underway, and it was one of the most phenomenal times that I remember to this day. And this program and NASA's return to the moon is, I think, just one of the most exciting things in this point in my life, and I am eagerly looking forward to seeing how this plays out. Thanks for all your participation in this.
Thank you. Yeah, I agree. It's very exciting, especially for me. I mean, I missed I missed the Apollo era, and I'm not that young either. I'm 32, so it's been a long time since anything like that happened, and I am really looking forward to seeing it happen again.
I'll tell you the truth. When that equal to Saturn, that Saturn V goes up, I am going to be down there.
Yeah, me too. I want to go.
I want to see that. That's going to be a hell of a rocket.
See it and feel it, right? You
I was
be
down
miles
there.
away and feel the vibrations.
I've watched every shuttle. Not every launch, but I saw every shuttle that went up at least once, including the 2 that were destroyed in the process. I was down there for night launches, day launches, you name it.
Nice.
And,
Yeah, I when I started at NASA, it was 2011, so I just caught the last shuttle launch, which was exciting but also disappointing. So I was really excited when the SpaceX Dragon just went up a couple months ago. It was really nice to see astronauts being sent up again.
I watched the year, the 1 year I was down there in June. The 2 Mars rovers were blasted off, and I was down there to see one of them. That was a rocket pack like I ain't never seen before.
Yeah. The other launch I'm looking forward to is the James Webb Space Telescope. If you're not familiar with that, definitely look it up. It's the successor to Hubble, essentially, but it takes images at infrared, and it's much larger than Hubble even, and it's been in development for quite a long time, but hopefully launching within the next couple of years here.
They had that Chandra that was, I don't know, whatever happened to that. That was an X-ray telescope. I was down there when that launched on. That was actually when the Challenger was it. Which was the one that blew up coming in? Was that was Columbia?
Challenger was in the 80s that exploded on launch, and then Columbia was
Columbia. That's the Columbia was the one that was the last launch that actually went up. You know, they launched again in January or whatever, and it ended up burning up coming back in.
Yeah, that's as I understand it, that's a big factor in this whole pre-staging approach, where you can have all your crew on one launch, and you can focus on launch abort safety and keeping things as safe as possible, and all the cargo goes up independently.
Hey, Mike, I have a question.
Mm-hmm.
On the Gateway supply vehicles, what happens to them once they've emptied their cargo? Are they coming back, or they just be jettisoned out into space?
Generally, they're disposable. Yeah, I wouldn't be surprised if SpaceX has plans to try and make them reusable somehow, but I don't see that being very feasible.
Okay,
just talking about like these logistics modules and things that carry up cargo.
Right.
Yeah.
Okay, thanks, Mike.
Mm-hmm.
Anybody else? Going once?
Yeah, Mike, this is Jim. I just wanted to thank you for spending your evening here with us. We really appreciate it.
Yeah, thanks. Hope it
Yes,
was entertaining and informative.
this was very entertaining. I do have one other question just popped into my mind. As far as the propagation goes, what does I know with us the sunspots has a lot to either negate or help the propagation quite a bit. How does that affect you guys?
That's a good question. I think for space missions, I think there's more issues with solar activity, like solar flares and things that could create interference. In my experience with like ground receivers and things, the atmosphere does shield us from a lot of that at the frequencies that we're talking about. So mostly we would consider the sun like a noise source if it's close to our receivers. But yeah, I think for the space missions where they're exposed to all that kind of activity, it's a much bigger concern.
Anybody else? On behalf of the Cuyahoga Falls Amateur Radio Club, I do want to thank you myself for spending your evening with us and
Thanks. Yeah, it was a pleasure.
Great presentation. It was really good. Can you give me my hosting back?
Yeah.
Forget that.
I will. Before I sign off here, I'll mention at the end here, I have some other videos that I thought might be interesting, and there's a couple in particular. This one here, I guess I'll send these links maybe to Jim, and he can forward them on to everybody. But this one is from Melissa McGuire, who is our orbital dynamics person on PBE. So she gave a really great presentation at this event where she talks about the orbital mechanics of Gateway, if you're interested in that. And what else? Yeah, so there's another nice fancy promo video narrated by William Shatner. I'm not sure how much we paid for that, but it's a very good video.
Sweet.
And then this is Orion as it was arriving in Mansfield for the testing that was done out at Sandusky. So it's really interesting to see this custom Super Guppy aircraft that they have to fly these things around. But you can really get a sense of how big it is and how difficult it was to transport it here and then drive it from Mansfield to Sandusky. And then at the, oops, can't play that. After, on the slide after this, there's another video by Dr. Robert Romanowski, who is our chief technologist for my division, the Intelligent and Communications division. He's a ham, and he gave a talk at the, what was it, Ham Sci conference. I'm not sure if any of you attended that. It was at Cleveland State, I believe, a couple of years ago. But he gave a talk called Crazy Antennas, where he talked about all the different unique antenna designs that he's worked on throughout the years. And that's on YouTube if you want to watch it. I was trying to bring him to do a talk as well, but unfortunately today he was tied up with something else. But I'm sure he would be interested for a future event if you guys would want to.
Yeah, we would definitely be interested in that.
All right, so let me pass control back here. I'm happy to, if you think of anything else too, I'm happy to make myself available by email or whatever if anybody has any questions.
Yeah, if you would, Jim, do you have his email?
Yes, I do.
Why
But
don't
actually, I think it's on the beginning of what you recorded too.
Okay.
Oh, yeah, that's true. It is in this presentation.
Yep, I'm back. All right. Well, if there's not anything else, anybody else have anything? We will go ahead and pronounce this closed. And thank you again. It was a great presentation.
Thank you.
Is our newsletter editor still out there, Bill?
I don't see him.
Okay, I've got some articles that I'm just about ready to send off. All right, thanks. Again, Mike, thanks so much. Really appreciate it.
Yep. Thank you.
And I'll leave the room open for a little bit. You guys can talk or whatever. I'll be here for a little bit.
Say we're rapidly diminishing here.
Let's see. Steve Searle, are you out in Arizona? What are you doing out there?
Thanks.